I'm Mindy Peterson, and this is Enhance Life with Music, where we explore the ways music can make our lives better and spotlight the resources you can use to enhance your life with music. In the last month, I've been hearing and reading so much about a groundbreaking study that was just published that explains new aspects of our brain on music, how music physically affects our brain through the laws of physics. I'm thrilled to have the chief author of this research with me today to explain the study, what the findings were, and what the implications are for the medical field and future treatment of a variety of conditions. Dr. Edward Large is joining me today from Connecticut, where he is a psychology and physics professor at the University of Connecticut and also directs the school's Music Dynamics Lab and the Theoretical Neuroscience Lab. He is a global thought leader in the psychology and neuroscience of music, with countless articles published in journals, including Journal of Neuroscience, Physica, and Psychological Review. And I happened to find out as we were speaking just before going on the record that he spent a lot of time in Boca Raton, where my daughter lives. So that was kind of fun to learn. Welcome to Enhance Life with Music, Ed.
Hi, Mindy. Thanks for having me.
Great to have you. Well, Ed, most musicians are familiar with the term entrainment. We've referenced that effect of music on this show many times. You've spent 30 years studying how music entrains or synchronizes brain rhythms, but this most recent study of yours takes this further. Tell us about your recent study that introduces neural resonance theory. We might be referring to this as NRT. How do you describe and explain NRT to those of us who are not scientists?
Yes. So, early in my career, I was really interested in understanding how people hear the rhythm in music. So how you can write down notes on a piece of paper that have sort of discrete duration. But when people play those back, they speed up, they slow down. There's all kinds of micro timing in the music. And I wanted to understand how that happens. And I hit on this notion of neural oscillation or brain rhythms. And the idea that brain rhythms might actually synchronize to music and enable the perception of the beat in music. That sort of blossomed into what was called dynamic attending theory, and this idea that attention is allocated rhythmically. So when you pay attention to something, not just music, but anything out in the environment, speech is another good example, that you listen for when important events are going to occur in time. So your attention is becoming entrained by music or by speech. And with this most recent study, what we're really saying is, look, it's not just what we call rhythm in music and speech. For music, it's almost every aspect of music that depends on the synchronization of neural oscillations, or what we call brain rhythms.
And I want to just repeat that neural oscillations term again, because I think we're going to be using that quite a bit. So oscillations are basically another word for the rhythms of the brain. Is that correct?
For the rhythms of the brain. So when we say rhythm, sometimes we think about the slow rhythms that occur in music and speech. But in neuroscience, when we say rhythms or oscillations, we can mean actually very fast rhythms.
Okay.
So oscillations that are as fast as pitches in music. So they could have hundreds or even thousands of cycles per second.
Okay.
So the idea then is that your brain is physically synchronizing with music at all these different time scales, at all these different speeds, different parts of the brain. Some parts of the brain are faster, some parts are slower, but these different parts of the brain are synchronizing with music at all these different rates. And the really important thing about that is that this allows us to sort of do the math and make predictions about, what does this say about how we're going to perceive the music, whether we're going to hear it as consonant or dissonant, whether it's going to be easy or difficult to learn to produce that relationship if we are musicians, for example.
Okay. One theory that I've heard a lot is that we enjoy music because of pattern sequencing, and our brain sort of resonates, for lack of a, I mean, we're going to be talking about resonating a lot in the physical sense, but in more of a like psychological sense, our brains resonate with music because there's this pattern and prediction that our brain
Mhm.
learns. We have like expectations of, it's almost like this fill in the blank type of thing. Like we
Right.
experience these different chord shifts in a certain sequence, and our brain sort of expect a certain sequence or chord to come next, and when it happens it triggers like this dopamine response, and we
Right.
feel pleasure because of that. And this NRT theory, this theory that you've been studying, if I understand correctly, it shows that what I just described is true, but it's only a small part of the story, and that our
It's
brains,
only part of this.
yeah, so our brains and our nervous system are actually physically resonating with the sound
That's
waves.
right.
Is that right?
That's right. So I wouldn't say for lack of a better word, because what we're saying is that resonance really is the right way to think about what's happening in music. So when an active rhythm in the brain or in the body, for example, so this is not just limited to the brain,
Okay.
but the brain is part of the body. So when these active rhythms are engaged, that itself is a mechanism of prediction. So that says, oh, something is about to occur right here. So prediction is part of the story. But when we sort of do the math and we look at the way that music affects the brain, what we see is that there is a sort of a pattern formation process that happens. And some patterns create really stable patterns in the brain, and others create less stable patterns in the brain. So it's really stability that's the issue. It's the stability of these patterns. And in terms of pattern formation, I mean, think about the processes that cause the spots on a leopard's coat. These are the kinds of pattern formation processes that I'm talking about. But now these patterns are changing in time, and they're changing from one pattern to the next pattern. So prediction, yes, prediction is part of the story, but it's only a little bit. If you think about, Chat GPT or, these large language models, one of the ways they work is they're just trying to predict the next word, trying to predict the next word. But because they have been trained on mountains of statistical data, they're really, really good at predicting the next word based on the context that has occurred before. And that's sort of the same prediction idea that's been applied to music. But what we're saying is for music, that's not enough. And in fact, one of the things that our theory says is some things are going to be a lot easier to learn for people than others, both in listening and to learn to enjoy something, but also to play it as a musician. And that's something that a theory strictly about prediction and about statistical learning doesn't predict. It predicts anything that's out there. If there's enough statistical regularity in the environment, you'll learn it. You'll learn that just as easily as anything else.
Well, what's really interesting to me, again, as a non-scientist, is that prediction, explanation, to me, that reflects on psychological resonance with music, whereas
Yes.
the NRT, that theory is more talking about actual physical resonance.
Right.
And what's cool about that is you can have, again, this is to my non-scientific interpretation of this, is you
Mhm.
can have somebody with dementia
Mhm.
who maybe they're not psychologically resonating with music. Actually, that's a bad
Mhm.
example because that musical memory is the last to fade away. And so they
That's
may
right.
still be resonating psychologically with music.
Mhm.
But if you take somebody who, for whatever reason, has a lack of psychological resonating going on in their brain when it comes to music, that physical resonance can still be happening.
That's right. That's right. So, I think one of the goals of neuroscience really is connect what's happening psychologically, what we see, what we feel, what we hear, what we think, to connect that directly to what's going on in the brain.
Mm.
And with neural resonance theory, that's sort of what we've done. We've said, look, we don't need any of these intermediate theories. We can go directly from what we hear and what we feel about music to what's going on in the brain, and we can make that link very directly. And
So that
really,
theory really demonstrates that this isn't just an abstract, subjective
right,
effect of music, but it's literally changing the physical state of the brain.
right, right. Because ultimately, I mean, I think most scientists would agree that what's happening in our brain really determines what we think, what we feel, what we hear,
Mm.
what we perceive, right? So,
What kind
yeah,
of differences do you see in this effect between live music and recorded music?
I personally haven't studied the difference between live music and recorded music, but a number of my colleagues have. For example, Laurel Trainer at McMaster University
She's been a guest on this
has
podcast.
she? Yes,
Yeah,
yes.
yeah,
So,
talking about lullabies. Yeah.
oh, really? Oh, that's great. I will have to listen to that episode. But yeah, and she finds better entrainment in the brain when people are listening to live music. So better
Okay.
synchrony.
Okay.
And it's fascinating because, it really goes to this notion that there's really something physical happening that explains our responses to music. And you can
Yeah.
feel it more, right? When you listen to live music,
Well,
you know?
that was one question that came to my mind as I was reading this research because I've always felt that when I go to a live, for me, classical music
Hmm.
concert, I'm sure that's very individual, but for me, when I go to a live classical music concert, I feel like it's a massage for my brain. Like I get out of there and I just feel like, like homeostasis has been reached
Hmm.
with my brain. And I've always wondered, like, what causes that? And is
Uh,
it because of the live music, or is it because, honestly, when I listen to recorded music, I tend to listen to very different music. It's not
hmm.
classical music. I like to play classical music myself on the piano. I'm a
Uh-huh.
pianist. I like to listen. If I'm going to live music, I like it to be classical. But if I listen to recorded music, I tend to gravitate toward other music. So I'm like,
Hmm.
is that why? Or is it because it's live? So that was something that was really
Well, you've
intriguing
got
to
what
me.
we call a confound. If you're listening to different music when you go live, then it's hard to tell, right?
Yeah, yeah, a confound. Haven't heard that
Yeah.
term before. Interesting. Well, one thing
It-
that was really
I'm just gonna a confound just it's when you change two things at once and then you try to figure out which one is
oh,
which one
not
goes.
good for
Yeah.
research.
Not we try to avoid that in research in
Right.
the lab. Yeah.
Yeah. Well, one thing that was also interesting to read in the research is you credit NRT
Mhm.
for music's side effect of the urge to dance and just what we
Yeah.
often call the groove. That
Right.
theory explains why people can also keep time, why
Hmm.
they can improvise music. And there was another effect that was interesting because people who have amusia, like they just don't. Well, I'll let you describe what's amusia.
So amusia is when people don't enjoy music. First of all, that's what they report. That's what they experience. I don't really
Is
like
that different
music.
than anhedonia?
No, that what I'm talking about is anhedonia right
Okay,
now.
okay,
So people with amusia experience musical anhedonia very often.
okay.
So I've talked to people with amusia. They'll say, "Well, my friends want to go to a concert. I don't really get anything out of it. I'm going with them because they want to go."
Yeah,
But then when they're tested in the lab, what you find is that they really have a very difficult time just differentiating between two pitches. So they have real deficits in terms of music perception. They don't perceive music the same way as we do.
and that would
Um,
be amusia. Am I saying that
right.
right?
Amusia. Yeah. Yeah.
Amusia. Got it.
Yeah.
So
And
amusia is basically like being tone deaf.
yes, that's the common term for it, right? And then there's
Okay.
a and then there's another aspect which has been discovered more recently, which is arrhythmic individuals who can't find a beat in music. And we all know people like this who can't dance, right? So it's the other side of the coin.
Well,
Um,
and just as an interesting side note, arrhythmia can be an indication of dyslexia and literacy. It can be sort of a
that's right.
predictor with real young children.
Well, yeah, so that gets into, this whole other sort of idea that brain rhythms aren't just important for music or for speech. They're important for everything we do.
Mhm.
So, cognition, perception, memory, brain rhythms of different frequencies and in different parts of the brain have been implicated in almost everything that we do as humans or as
Interesting.
animals in general, actually. Yeah.
Interesting. Well, I've sort of led us on a few different tangents there, but back to the anhedonia. Musical anhedonia is basically people who don't get pleasure out of music. It just doesn't really do anything for them. Amusia is more what we consider someone who would be tone deaf. NRT can still apply to those people because of this physical resonating of their brain, of their nervous system with music.
Right.
And I think I saw in the research that really it's a very, very small slice of the population that truly is tone deaf or truly has amusia. Is that right? Like
Right. That's
1.5%
right.
or something like that?
Yeah, I think a little bit more, like 5 maybe, it depends. The estimates really vary, and it depends actually on who you're testing. But yes, a very small percentage of the population. And the thing is, NRT makes really interesting predictions. It predicts that there are very simple reasons why people might experience these conditions, which sort of boils down to the strength of connections between different parts of the brain. So, neural resonance theory is about nonlinear resonance, really, in the brain. And the strength of nonlinearities depends on the strength of stimulation. So the more nonlinearities, the more stimulation, the more complex the patterns that form. And if you don't have enough, those patterns that the brain relies on for music perception might not form at all. So you might not be able to hear the beat. You might not be able to identify the pitch. You might not be able to hear consonance or dissonance of harmonies the same way.
Well, it's really intriguing that this neural resonance theory really shows that the human body is very much part of this music listening or music making process.
Mm-hmm.
And I think I saw in the articles that I read, neurons vibrate almost like a plucked guitar string. So there is this physical resonance.
Mm-hmm. That's right. That's absolutely right.
So what does that mean? What are the implications of this in terms of, like, what do we take away from this research, especially in the medical field? Because I know that you've really translated these findings into some therapeutic tools. So tell us what the implications are of this study.
Right. So, as I started to say, brain rhythms are important for almost everything that we do. And one of the things they're very important for is memory.
Mm.
Memory and cognition, in fact. So in the hippocampus, which is the brain's sort of memory center, when we retrieve a memory, neurons have to synchronize at a particular rate. They have to resonate with one another, not necessarily with the outside world, although that happens as well, but they have to synchronize with one another. And they synchronize in a frequency range that's called the gamma band. It's a range around 40 cycles per second. And it turns out that when people develop problems with memory, like in Alzheimer's disease, one of the things that happens is that resonance, that self-resonance, that synchronization at the 40 hertz rate is weaker. Those neurons aren't synchronizing. So one of the ways you can think about it, and this brings us back to resonance a little bit, is think about the brain not so much as a computer, which is a very common metaphor. Think about it as like a radio. Two parts of the brain have to synchronize to exchange information. So just like a radio, you have to tune to the right frequency before you receive the right radio station. Okay. And then you can start getting the information from them, right? That's exactly what happens in the brain. When different parts of the brain have to exchange information, they synchronize.
Okay.
And this is one of the things that goes wrong when we start to, our memory starts to deteriorate in conditions like Alzheimer's disease.
Okay.
So what occurred to us, and by us, I mean my colleague Psyche Louie.
She's been a guest here on the show
Kim.
too. So she's working with you on this.
She is working with me on this. In fact, this idea of applying neural resonance theory to treat Alzheimer's was her idea.
Okay. Well, that's interesting because as we've been talking, I've been thinking about my conversation with Brain FM, and they really have used similar concepts to really scientifically design music to achieve certain brain states, whether you want to focus, whether you want to sleep, whatever it is. And so this would have huge significance for what they're doing as well. I would think, and I know Dr. Louie has been very involved in Brain FM as well.
Yes, that's right. She has. So what Psyche, Dr. Louie, came to me with one day was some research from MIT that showed if you rhythmically stimulate neurons in the hippocampus directly in mice that have Alzheimer's disease, you can lower their amyloid beta plaque load. These are the pathological proteins that develop in Alzheimer's disease. you can lower that plaque level by 50% and you can improve the memory in those mice.
Oh, wow.
And the researchers at MIT had started experimenting with, well, can we just do this with sound and light? And they found, yeah, we can. And what Psyche said to me is, well, as you know, Ed, the best stimulus for synchronizing brain rhythms that we know of is music. And she suggested that if we combine music with synchronized light, we might have an effective music-based therapy for Alzheimer's.
Yeah, let's talk about that some more here, because I know you're actively working on developing something with your company, Oscillo Biosciences.
Yes.
Before we do that, I
right.
just want to quickly let listeners know about some of the other conditions that you see music being able to better treat as a result of this study. We touched on Alzheimer's, and we're going to go back to that. What are some other conditions that you think could be better treated with music as a result of?
Well, in principle, any neurological dysfunction or psychological dysfunction that's associated with a dyssynchrony of brain rhythms.
Okay,
And a lot of them are.
so Parkinson's disease?
Parkinson's. So Alzheimer's turns out to be sort of a not enough synchrony in certain parts of the brain. Parkinson's is the opposite. It's too much synchrony. So the key there would be to disrupt pathological synchrony in certain frequency bands.
Okay.
As you mentioned, dyslexia and problems with reading are associated with problems with synchronizing with musical rhythms. So by priming people with musical rhythms, or children, or asking them to tap musical rhythms ahead of doing, for example, a grammatical task, it improves their ability. So I think each deficit requires its own sort of research and its own careful study in order to understand what's the best way to use music. But I think what I would say is that we're beginning to understand that it's possible not to use music only to help you sleep or to help you focus, but we could potentially treat serious neurodegenerative diseases with music. And that's what we're trying to do at Oscillo Biosciences.
That's really cool. I mean, it totally makes sense. I know I've used electric stim before, whether it's at a chiropractor's office, or now you can buy these TENS machines and sort of do it yourself. And to me, there's a lot of correlation there where it's like, well, yeah, I mean, if that works, then this should work also. I think I also saw some other conditions that could be treated, ranging even to something as broad as depression and anxiety.
Yes, that's right.
MS and educational implications. You mentioned dyslexia and other literacy skills.
And actually, schizophrenia even is associated with dysynchrony of gamma frequency rhythms.
Interesting.
So I have a student. I was on his PhD committee. He just graduated, and he's been looking at implications for schizophrenia.
Wow. Fascinating. Well, and we've talked on this show about a lot of these conditions and how music can already be used to treat and be an intervention for MS, for Parkinson's, for mental health, Alzheimer's, things like that. But this neuroresonance theory will just jumpstart all of that and just give that, additional lens and application.
What it really says is that we think we know sort of the active ingredient of music that's doing the job.
Sure.
Right? If you've seen, there are a number of different documentary films out there about the effect of music in Alzheimer's disease.
Yep.
You may have seen Alive Inside, or there's a documentary about Glenn Campbell, which I don't remember the name of right now. And, the sort of the upshot of those is that music seems to have this almost magical effect on people with Alzheimer's disease.
Yeah. Tony Bennett as well.
And Tony Bennett and Lady Gaga. Yeah, that was a beautiful documentary. So maybe, we don't have to just think about it as, sort of a magical effect of music. We think now we know what the music is doing, and we know how to sort of supercharge it by combining it, in our case, with synchronized light.
Yeah. Staying balanced in life is very important to me. Balance in work and play, activity and rest, and balance in fueling my energy. When I am on the go or just find my cupboards running a little bare, the fuel I reach for is Jam Bar energy bars. These bars are certified organic whole food bars. They're non-GMO and gluten-free. I especially love that they are higher in protein than the other all natural bars I found, and they're minimally sweetened with only all natural sweeteners. Well, I love all five flavors. My personal favorites are musical mango and tropical trio. Jambar flavor names reflect the company founder's passion for music. And Jambar donates a whopping 50% of net profits to programs that support music and active living. Join me in supporting a balanced life and world by reaching for Jambars. Available at Amazon, select retailers, and jambar.com. Links are in the show notes. Well, let's talk some more about what's happening in applying this research therapeutically. Alzheimer's is sort of the first frontier that you're tackling, doing more
Yeah.
research. You mentioned working with Dr. Seki Louie on some of this, and also I think you're co-author of the neuroresonance theory paper. I'll let you say
Dr.
the name.
Jichul Kim.
There we go.
Jichul Kim. Yeah.
I knew I would mispronounce that.
Yeah.
So you've developed a healthcare startup, Acelo Biosciences. Tell
That's
us a
right.
little bit about that and what you're up to with it.
Well, we started out just developing a system that would synchronize lights to music, and it synchronizes really in two different ways. First of all, it synchronizes in the theta frequency band, which is about 4 to 8 cycles per second. And then it produces pulses of light in the gamma frequency band, which is about 40 cycles per second. And it does that in a certain way. So every 4 cycles, or every 4 times per second, let's say, or 5 times, in that range, it produces a pulse of gamma, which is about 40 cycles per second. And in doing this, the idea is to stimulate theta gamma phase amplitude coupling, which is a mouthful. But this is the way that frontal and temporal regions in the brain communicate with one another during cognition and memory tasks that we can run in the lab. So we know this. So we're stimulating gamma, as we said, but we're also stimulating theta and the relationship between the two. So we first, experimented with that, and we saw that indeed it has the effect on the brain that we wanted it to have. And then for the past couple of years, we've been running a phase 1 clinical trial in Psyche's lab at Northeastern University, and we've been getting some really interesting results. So the first thing that, we ask is, do people like it? Because it's music, and actually the great part about it is people get to listen to their own favorite music. So they get to pick the music. Doesn't have to be special music. It could be whatever's on there.
It can't really. Like, there is no one size fits all when it comes to
right.
music, right?
That's right. So they pick their own favorite music, but they're also listening to these flashing lights, which, you might think it would be a little bit annoying. And our control condition is podcasts. So they listen to podcasts, and there's some lights that are synchronizing, but not in theta and gamma frequency bands. And it turns out that people like we call it synchrony gamma. They like synchrony gamma therapy better than the podcasts. No offense. I like podcasts. But they like synchrony gamma better. So they listen to longer than we ask them to. We ask them to listen to 30 minutes a day for eight weeks. They listen longer than required almost every day. So 54 out of 56 days, they listened longer than 30 minutes.
And when they say they like it and they want to keep listening, what is it that they're liking? Like, do they just feel relaxed, or like, what are they liking? They like the effect afterward, that they can
They like the music,
more?
but they like the feeling, I think, that the therapy, they realize that there's a therapeutic effect. It's a very strong effect. When you put on those lights and they're synchronizing to music, you get a really strong effect. You can definitely feel that something is happening.
Okay. And then the idea is that whatever effect is created continues after the lights and the music are turned off.
That's right. So I can tell you that people listen to synchrony gamma for 37% longer overall than we asked them to. People have asked us if they could keep the device and continue the therapy afterwards, which of course we say yes. And there's even one of our subjects started blogging about how wonderful it was.
Oh, interesting.
So
how far are you? How far are you in this clinical research phase?
We've got 22 patients who've completed the study, and our goal is to get 60 patients. So that'll take us another year or maybe a little longer. So we should have final results, but we already have enough subjects to see some results. So what we know for sure is that we are stimulating theta and we are stimulating gamma in the brain as we want to. We are stimulating theta gamma phase amplitude coupling. But really, the important thing is we're improving their memory. So we've got a very large effect. The people who are in the control condition, their memory is decreasing over the 8 weeks, and the people in our synchrony gamma condition are increasing. So their memory is actually improving. This is a large statistically significant effect. So we're very excited about that.
Oh,
Um,
yes.
the other thing we've been able to show is that this increase in theta gamma phase amplitude coupling that we're after in the brain actually correlates with that improvement in memory. So for all the subjects in both conditions, with their theta gamma phase amplitude coupling goes down, their memory gets worse. If it goes up, their memory gets better.
Wow.
And the final thing that we're showing is that this phase amplitude coupling also predicts an increase in activity in the hippocampus, the brain's memory center. So, and that explains, again, this improvement in memory. And we haven't published our journal article yet. We're working on it now. But many of these findings have been described in presentations over the past year. And we'll describe more at a conference down in Brazil this summer. We'll describe these results that I just mentioned.
Wow.
Yeah.
And no side effects, no interactions with other medications to worry
That's right.
about. I mean,
That's right.
it's
And potentially you could use it. It could be complementary. You could use it with a medication if they're
Sure. Well, and I can just see so many. I know this is specifically designed for people with Alzheimer's, but I have a mother who has a traumatic brain injury from a car accident that she was in, gosh, decades ago. And once you have this down for Alzheimer's, I can imagine really great transfers and uses, applications with people with traumatic brain injuries and then
Yes.
other memory issues. I'm a woman, so I think about pregnancy brain,
Mhm.
menopause brain, like,
Yeah, right.
yeah, let's go there next.
Right. I think, yes. So once we get it to work for one indication, yes, let's try it for lots of others and see if it helps.
Yeah.
I don't know right now if there are any studies in terms of synchrony of neural oscillations in mommy brain or in traumatic brain injury, but they may be there and they just haven't been noticed yet.
Sure. Yeah. Well, with this addition of the light
Mhm.
show that's going on
Mhm.
as they're listening to this music, do you know what correlation there is to EMDR? Are you familiar with that? With EMDR form
No,
of psychotherapy? No?
no.
It's a psychotherapy where it's talk therapy, there's no music
Mhm.
involved, but the patient has typically 2 tapper type things that they're holding. So
Okay.
it's a kinesthetic and visual stimulation that it's bilateral, it
Mhm.
alternates.
Mhm.
So the tappers will vibrate and also light up.
I see.
And so as you're talking and thinking about different memories, or it's especially used in trauma,
Mhm.
you're holding these 2 tappers and they're bilaterally, alternatingly vibrating and lighting up. And so your
Mhm.
eyes are going back and forth. You're having that kinesthetic back and forth stimulation with the buzzing, the vibrating.
Mhm.
And it's been found to be very effective with trauma. And so I was just wondering if there's any correlation to what's happening through that therapy.
I don't know, but it sounds like there might be. There are people. There's one really wonderful researcher out at the medical school at Stanford. His name is Peter Tass, and he's looking at vibrotactile stimulation for Parkinson's. So we mentioned that Parkinson's has hypersynchrony of beta. We didn't mention beta, but beta oscillations, and he's using vibrotactile stimulation to desynchronize those pathological oscillations using an algorithm that's very similar to the algorithm that's used actually in deep brain implants. But, again, he's looking, as we are, at treatments that are non-invasive and that are
Yeah.
not aversive for people.
Well, I love on the Acilo Biosciences website, there's a section that says, "Why music?" And then it
Yeah.
lists several different superpowers of music and why
Yeah.
music is uniquely situated to help with some of these different parts of the brain, dysfunction of the brain. It's a unique access point in the brain. It's just this whole list of things. So I encourage people, there will of course be a link in the show notes to that website where people can look through those. I know we're out of time here. This has been so fascinating. Is there anything else before we close out with a coda that you just want to leave listeners with, or want to make sure that they know that we didn't get a chance to discuss or highlight?
Mindy, I think you've done a great job of, really bringing out all these, implications of neural resonance theory, and especially for therapeutic uses. So,
Okay.
no, you've done a great job. Thank you.
Okay, good. Well, all the best to you. I wish you the best success with your work on the clinical study and coming up with an application and intervention for Alzheimer's disease, and then hopefully some more applications after that.
Yes.
Well, as you know, I ask all my guests to close out our conversation with a musical ending, a coda,
Mhm.
by sharing a song or a story about a moment that music enhanced your life. Do you have a song or story you can share with us in closing today?
Well, yeah, the song that I would like to point your listeners to is a song called Superstition by Stevie Wonder. If you turn on this song and you listen to this song, first thing you're going to notice about it is it makes you want to move. It
Mm.
makes you want to tap your feet. It makes you want to shake your hips, or maybe even just full on get up and dance. And the thing, that I think is important is to ask yourself why that happens. Why is it that that song in particular, or songs that, have that sort of groove, we call it groove. Why do those songs do that? And what we've discovered and sort of tried to make very clear via neural resonance theory is that some songs that have just that right level of rhythmic complexity give you the strongest feeling of a beat in music. And we've now, working with our colleagues in France, Ben Morion and Danielle Schön, we've actually been able to show the parts of the brain that are synchronizing with music that has a groove like that. And the reason I specifically point to Stevie Wonder is because one of my colleagues who is early on in the research on groove, Peter Giannata out at UC Davis, he did a study and he asked undergraduates, and this was about, I don't know, more than 10 years ago. So not that long ago, to rate, all these different songs on groove, how much they wanted to make you move. And even though that's the song from, was it the 60s or early 70s? It made the undergraduate students at UC Davis want to move most out of
Oh,
all the
really?
songs and 10 years ago. So, it works for any generation, I think.
Oh, wow. So listen to Superstition by Stevie Wonder to experience neural resonance theory in action in your own
That's
body.
right. Exactly. Exactly.
You can listen to Stevie Wonder's Superstition in the show notes to experience neural resonance theory in action for yourself. Thanks so much to Dr. Large for all he does to enhance lives with music through his work and research, and for joining us today to explain NRT and why it matters to those of us non-scientists. As always, you'll find lots of links in the show notes, including a transcript of our conversation and related episodes you may enjoy, including the episodes we mentioned with Ed's colleagues Laurel Trainer, Psyche Louie, and on Brain FM, as well as episodes on music's therapeutic application for Parkinson's disease, multiple sclerosis, and other conditions. All Enhanced Life with Music episodes are evergreen, so check out the back catalog for more ways that music can make your life better. You can always connect with me on email, mindy@mpetersonmusic.com, Facebook, Instagram, X, or LinkedIn. Thank you so much for joining me today and for sharing the show. Until next time, may your life be enhanced with music.